I'm working with the NWT 200 again. I showed this hookup in part 1, but I didn't adequately describe it. This is a 1 megahertz quartz crystal. It's connected in series with the input and the output. I'll do a single sweep. And here you see a blip at 1 megahertz. And it's a positive going, if you will. It's a higher amplitude than the baseline. I should say something about the speed of the trace. The number of samples per sweep I have set for 9999. I'm going to set it for 1000. I'll do another sweep. It will be a much quicker sweep. But you see the blip that we expected at 1 megahertz? The steps are such, and the steps right now are 2500 hertz wide, that it just sort of passes over a sharp blip. It would be fine for doing a bandpass filter, for example. But a crystal or some very narrow pulse is not fully expressed at the low number of samples. And there we have the nice blip. Right now I've got the sweep ending at 3 megahertz. I'm going to take it down to 1.5 megahertz. I guess I can't put a decimal point. I've reconnected the crystal such that the input and output are looped together, and the crystal is shunted across between the center conductor and the braid. And I'll do a sweep. And it's just not there. And you see there's absolutely nothing showing at 1 megahertz at all. What I have here is a parallel circuit. It's 220 picofarad capacitor in parallel with a nominal 1 microhenry inductor. And it's the capacitor and the inductor are in parallel, and they're in series from the output to the input. I'm going to do a single sweep. I've got it set for 500 kilohertz beginning and 100 megahertz ending. Do a single sweep. See where it's resonant. That's a nice resonant circuit. I'll take this down to 30 megahertz. Do a single sweep. Now, the inductor in this case is variable. I'll show you what a smaller sample rate does. I'm going to change that sample rate to, say, 1,000. I'll do a single sweep. I said it was pretty fast. Let me put it on continuous sweep. Okay, so it's going to redraw as fast as it did the single one. It's going to perpetuate itself. I'm going to adjust the inductor now. And you see how we can see it tune. So that's where a high sample rate is not good. If you're going to tune something and you want to have some sort of response, you need to set a low sample rate, a quick sweep. And once we're in the continuous mode, you can see the cursor here showing the progress of the sweep. So I have to stop it using the stop button. So it'll finish that sweep. I have this little SV1 AFN amplifier. It's a single 2N5109 transistor. I have the output from the sweep oscillator hooked to the input. I've taken the output from the amplifier, put it through a 20 decibel attenuator and to the input. Because I've put 20 dB of attenuation here, I told the program there's 20 dB of attenuation in this display shift box. And what that did was turn the decibel scale red, and instead of 0 or dB being at the top, well, 10 dB being at the top, now it's 30 dB. It allows for the added 20 decibels. Additionally, I've set the internal attenuator to provide a minus 20 dB output. I'm going to do a sweep with the power off. I'll do a single sweep. So the best we're doing is about 40 dB of output power when it's not turned on. See what I did there? I moved the cursor. I can just arbitrarily put it anywhere I want. So there we go. I'll put the cursor there. I'm going to power the amplifier up. So the amplifier is powered up at 12 volts and 40 milliamps. I'm going to do a sweep now. The current did not change. But where we had 40 dB of output, we now have about, we're in minus 40 dB of output. We now have minus 5. So that gives us 35 dB of gain in this little amplifier. I'll remove the 20 dB attenuator. That is the one that's inside the NWT unit. And I'll do a single sweep. I've got the output hooked to my oscilloscope. I've got it set to sweep from half a megahertz to 200 megahertz. You can see the amplitude falls off, but this is only a 200 megahertz scope. So I would expect it to be down 3 dB at 200 megahertz if it were perfectly uniform output. I'm going to set now for a VFO, actually a fixed frequency. I'm going to stop the sweep first. I'll go to VFO. And this is, or should be, a 10 megahertz sine wave. And my little frequency meter on the oscilloscope says 10 megahertz. Now you want a fairly good sine wave, that's spectral purity, when you're doing a look at when you're intending to look at filters or resonant circuits. A square wave or a poorly developed sine wave has lots of harmonic energy in it. This should be a 200 megahertz sine wave. My frequency meter says 199999. That's pretty good for an oscilloscope frequency meter. I'll set it to 14 megahertz because that's a default. Of course, it's way down here. My oscilloscope says 13.9999. Change that to 114 megahertz. Again, the frequency meter says 114.000. So and I can vary this in 1 cycle steps according to the software. I can also insert 10 dB of attenuation. There's 10 dB. There's 30 dB. I cannot attenuate in any finer steps than 10 dB. The output can be 0, minus 10, 20, 30, 40, 50.